This is 2018 AMC 12B problem number 25, and here is a view of this problem. We are given three circles, omega 1, omega 2 and omega 3, each with radius 4, and you can also see it clearly on our sketch. These circles are placed such that they are externally tangent to each other. The points P1, P2 and P3, as you can see here clearly on the picture, on each of these circles, omega 1, omega 2 and omega 3, are such that P1, P2 is equal to P2, P3, which is equal to P3, P1. In that sense, you can say that triangle P1, P2 and P3 is an equilateral triangle. Sure. What else? And also the line P1, P2, P2, P3, and P3, P1, which again are the sides of this equilateral triangle, are tangent to each of these three circles. So for instance, our triangle P1, P2, P3, if you extend this one, it would be tangent. This is a point of tangency, and so on. So if you extend this, you have a point of tangency between P2, P3 and the circle omega 2. And the same way here, you extend this one, you have a point of tangency here. Finally, the area is what we are interested in figuring out. So P1, P2, P3. Because it's an equilateral triangle, all we need is basically the side length of that triangle. So therefore, if we can find, say, P1, P2, the side length here, then we can plug it in to find the area of this equilateral triangle clearly. Okay, so let's first start by marking the centers, which you can easily identify by extending these perpendiculars and eyeballing where that location might be. Let me go ahead and extend this perpendicular as well. That doesn't look like it's the diameter, but you guys get the idea. So I can eyeball it probably here. And just for the record, you all remember, so if you call it center of circle 1, this is the center of circle 2. If you connect the two centers of these tangent circles, obviously this line segment joining the centers will go through the point of tangency between those two circles. Okay, going back to our story, so we really need to calculate P1, P2. So how can we do that? So far all we know is the, if you call this point as T, for instance, we know the radii of each circle. And so this is 4, 2, this is a 4 again. What we have is we will use the standard usual trick and extend these lines to get some new circles, right? We do it quite often when we use, say, similar triangles or this type of settings. So this point, let's call it as S. Let's try to do some angle chasing. For instance, we already know that this is an equilateral triangle, so this gray angle is 60 degrees, suggesting that this one is here 30 degrees. What else? What else do I know? Yes, so, this is a 90-degree angle, obviously, right? So, that's how convenient. We have a 30, 60, 90 triangle here. So, if you call this distance P1S as D, let P1S be equal to D, and in that case, we can easily find, and so this implies then P2S, which is associated with the hypotenuse of that triangle, would just be double that thing here. So it would be 2D, right? And finally, and P1, P2, P1, P2, P1, P2, opposite 60 degrees, so it would be root 3D. And this is actually what we need to what we needed. So the question, we boiled down the question to calculating the D. If I calculate the D, it will give me P1, P2, and in turn P1, P2 will give me the area of this triangle P1, P2, P3. So how can I measure those finally? Let's see. So we mentioned this whole thing is root 3D. We have a D here, we have a 4 here. Yeah, so that no, sorry, 4 is TO2. No, we don't know what P1, P2 is, so that's not a very good idea. Instead, let's focus on triangle, say, O1, O2S. So yes, definitely. So we will apply law of cosine on triangle O1, S, O2. That should do it. We know what O1, O2 measures. O1T is 4. O2T is also 4. So that's good. Yeah. So apply a law of cosine on a triangle O1, S, O2. Yeah, and we will do it with respect to this angle, which is 60 degrees. So we would get 8 square equals 4 plus d square plus, this is O1s. O2s would be, the whole thing is root 3d, so therefore it would be O2s would be root 3d minus 4. Oh no, that's not the case, because we have a 30, 60, 90. This is opposite the 90 degrees. Oh my, that's 2D. Oh gosh. The root 3D is P1, P2, which I said it here earlier. Silly me. Okay, so 2D minus 4 square minus 2 times 4 plus d, 2D minus 4, and then cosine of 60 degrees, the angle between the two. Recall that cosine 60 is 1/2, so it would cancel out with this 2 here. Alright, so the rest is just finishing the calculation. So 8 square is 64 equals, let's just expand everything out, 8d plus d square plus 4d square minus 16d plus 16, and finally we have minus, we have 8d minus 16 plus 2d square minus 4d. Alright, so let's hope that we will get a simple expression here. So we have, let's see, well, plus 8d minus 8d, they cancel each other out. So I have 64 on the left hand side as a constant. I have 16, another 16, so 32, another 16, 48. So we would have 16 left on the left hand side. We have d square, 5d square minus 2d square is 3d square, and finally we have minus 16d plus 4d is minus 12d. Actually, it's better to just bring the 16 to the right hand side as negative 16. I hope I haven't made any silly mistake here. And now you can make use of quadratic formula, obviously. So let's try it. So this implies that d is equal to, obviously I need the positive length, so 12. Well, I don't know which one is the useful one, but probably the positive one. Let's just keep both of them for the time being. So 144 minus 4 times 3 times minus 16. Yes. All divided by 2 times 3. So this finally implies that d is equal to, so 12 over 6 is just 2 plus or minus. So we have one inside the radical, we have 48 times 4, 96, 192, so say 200, 336. So square root of 336, that seems a quite familiar expression. Let's factorize that 336 monster. That would be 2 times 168, 2 square times 84, 2 cubed times 42, 2 to the 4 times 21, 2 to the 4, 3, and 7. That wasn't what I exactly expected, but I guess better than nothing. So I can factor out the 2 square outside, so we will be left with 2. Yeah, I will need the positive one for sure. And then when the 2 square come out, let's just keep it out. I have a 21 here. I have 2 times 3 here. The 2 and the square will go away, and that's it. That's the distance d. Now P1, P2, recall, is simply equal to, if you recall, that's just root 3d, because on that 30, 60, 90 triangle P1, P2, S, you can clearly see that it's opposite the 60-degree angle. So it's root 3 times d, which is equal to root 3 times this ugly expression, 2 plus, I think we found 2 over 3 root 21, and that's simply equal to 2 root 3. So root 3 and root 3 will be 3, they will cancel out with the 3, it will be 2 root 7. Whew, so we have the side length of our equilateral triangle, so it shouldn't be too hard now to finally compute the overall area of that triangle as simply the square of this expression, 2 root 7 square root 3 all divided by 4. When you finally expand all this and do the simplifications, I believe we get 10 root 3 plus 6 root 7, which is simply equal to, because the question is clearly asking to give us in this format, we need to bring the 10 and the 6 inside the square root, so we would have square root 300 plus square root of 6 squared is 36, 36 times 7 is 252, and boom, so square root 300 plus square root 252, so 300 plus 252 would be 552, and we are done with this problem as well.